Hello, in today's video we're going to be talking about polar molecules, and this is going to be a continuation of the polar bonds that we saw earlier in the week. So let's review what a polar bond is, and then let's extend this to the world of molecules. Let's take a carbon-oxygen bond, just a single bond, carbon to oxygen. We know that oxygen has a higher electronegativity. And the reason why we know oxygen has a higher electronegativity than carbon is because oxygen is closer to fluorine. And the trend in electronegativity increases as you go from the bottom of the table to the top of the periodic table. And it increases going from the left of the periodic table to the right of the periodic table. So oxygen has to have the higher electronegativity. And what that means is that oxygen is better able to steal electrons, to have the electrons surrounding it, than carbon is. And what we end up getting is something called a dipole moment. We know that the oxygen becomes partially negative. The electrons are surrounding it more often. The carbon has fewer electrons surrounding it, or it has electrons surrounding it, but not as much. And so this becomes partially positive. So we can denote a dipole moment by drawing an arrow going from the positive side to the negative side. And we put a little plus at the positive side of the arrow, on the arrow, and we put the arrowhead at the other side. So this is our dipole moment. We know that this is called a polar covalent bond, and this is our understanding of how electronegativity what part it plays in a bond. Now let's extend this to a molecule. Let's look at the HCN molecule, and let's see if that is a polar molecule or a nonpolar molecule. HCN. This is the Lewis dot structure for the HCN molecule. The way that we figure out if the entire molecule is polar is we have to identify if each bond is polar, and then we have to do a quick comparison of the relative intensities of those dipole moments. So let's see, H and C. We know that carbon has a higher electronegativity than hydrogen, so we're going to get a plus arrow going this way. So this means that carbon has these electrons surrounding it more often than the hydrogen does. Now we have to take a look at the carbon-nitrogen bond. Well, nitrogen is closer to fluorine than carbon is, so nitrogen has to be better, it has a higher electronegativity. So what that means is, for this bond, the carbon-nitrogen bond, we get an arrow going this way. Now we're not going to actually have the true numbers of the dipole moments. We're just going to have relative sizes of these arrows. And what we can see is that both of these arrows point from left to right, and this is a linear molecule, so we can draw the overall dipole moment of the molecule as an arrow going from left to right. So the HCN molecule, what we did is we broke apart each of the bonds, we saw if it's a polar bond or not, and then we kind of added those arrows together. And in this way we can see that this is definitely a polar molecule. If you end up with an arrow as your dipole moment, your total dipole moment, that means that the molecule itself is going to be polar. Okay, let's take a look at another one. Let's take a look at something else. Let's look at the nitrogen molecule, just N2. We know that the N2 is going to look like this. We know that this is not going to be a polar bond or a polar molecule. Both of these nitrogens are pulling on those central electrons the same, so this is a non-polar molecule. Okay. This gets a little, so this one was easy. It's just a diatomic. Now if we move up to something a little bit more strenuous, let's look at the CH4, methane, CH4. This is a little bit more tricky. We can easily draw the Lewis dot structure. We've been doing that for a while now. So the Lewis dot structure for methane looks like this. Now, in reality, we know from VSEPR theory that the bond angles between each of these hydrogens, the bond angles, is 109.5 degrees. And what this shows is that each of these HH bonds is this is called a tetrahedral structure, and we know that each of these bonds are in the exact same location. So if we were to draw our dipole moments for each of these bonds, each of these 4 HC bonds, we would get an arrow going in from this one, an arrow going in from this one, an arrow going in from this one, and an arrow going in from this one. Now if we were to add up all of those arrows, they would all cancel each other out. The downward or the upward part of this arrow cancels out with the downward part of this arrow. The left part of this arrow cancels out with the right part of this arrow. So this molecule is non-polar. Now, in reality, we know that the methane doesn't look like a square, it looks like a tetrahedral structure. So we have to be able to look at a 2-dimensional surface and picture the 3-dimensional world to be able to draw these arrows. So this is a non-polar molecule. Let's look at one more example. I'm going to give you a big table that breaks down all of our Vesper theory notation into polar and nonpolar molecules, but I want you to be able to do this on your own. Let's look at the CH3Br molecule. So this is slightly different than what we had in the methane. We still have the central carbon, it's surrounded by hydrogens, but in this case we have a single bromine surrounding that, attached to that carbon. So let's draw our dipole moments. We have a dipole moment going this way, a dipole moment going that way, a dipole moment going that way, and then for the BRC bond, we have a dipole moment going from the C up to the BR. What this means is our left and right hydrogens cancel, but we now have 2 arrows going from the bottom to the top. So we have an overall dipole moment looking like this. What that means is the CH3Br molecule is going to be polar. It's a polar molecule. However, it's not going to quite look like how I drew it here. We have to think about this in 3-dimensional space. So really I can redraw this. It's going to be my attempt at drawing a 3-dimensional surface in 2-dimensional space. It kind of looks more like this. If we bend the bonds a little bit better. This hydrogen is kind of going into the board. These 2 hydrogens are on the plane of the board. This hydrogen is kind of going into the board, or this bromine is kind of going into the board. What we end up getting is a dipole moment going in this direction. We still have an overall dipole moment. We have a polar molecule. So your goal will be to identify each of the bonds, see whether each bond is polar, and then add up the arrows just visually, because we don't have numbers for them yet. Add up the arrows in your head to identify what cancels and what doesn't cancel. And then see if there's an overall polar aspect, a dipole moment in the molecule. So tomorrow in class I'll give you a big table on our about our Vesper theory notation that allows us to predict polar and nonpolar bonds. But with that, that's all I want to say. I want to say have a great night, and I will see you all in class tomorrow.